Alright, in this video we're going to compare Stokes' theorem and Green's theorem because they do seem awfully similar. So first thing in Stokes' theorem, when we look at this, the left-hand side is a vector line integral, right? So this is a vector line integral, okay? And this is talking about circulation, so we're looking at kind of global circulation around the boundary. Okay, so that's really all that left side is telling us. And in Stokes' theorem, the right-hand side, well, we know that this is a vector surface integral, right? So this is a vector surface integral, okay, which we called the flux, so it's computing flux, which really is adding up, okay, with the effect of the double integral, adding up all microscopic rotation. Okay, and so we're saying that these two things will be the same. And then also notice that when we're using Stokes, this is S is a surface in R3. Okay, when we look at Green's theorem, this is saying that this left-hand side, okay, it is a line integral. It is a vector line integral around the boundary. Okay, so this is, again, still looking at global circulation around the boundary. And on the right-hand side, this is our surface area, right? So it's adding up. Well, it's a scalar of the surface area, but it's adding up all microscopic rotation. Okay, and the only difference here is that when we talk about D, this is a region in R2. Okay, so seems to be that they're very similar. And so here's the next question we're going to think about is, okay, so if we have the boundary of D, or dd, del D, it's oriented in such a way that Green's theorem applies. So if Green's theorem applies, we would be progressing in this direction. And so what we can do is just view this as a surface in R3 that is sitting in the xy plane. Okay, so z is 0 in essence. Okay, and then when we think about this, so if we think about an orientation of the surface D, what orientation would we need to have so that the boundary is consistently oriented? And so pause the video and see if you can answer that. Well, if we think about this, I think what we see is that, okay, when we look at the orientation, it seems like this would need to be the direction in which we would progress locally for any normal vector. And when we sweep our fingers in that direction on our right hand, the normal vector actually points upwards, right? So that would be the positive z-axis. That would need to be our normal vector. Okay, and that would need to be the orientation of the surface. Okay, but really all this, and then in that case, then we could apply Stokes' theorem. So the punchline here is that Stokes is a generalization of Green's. Okay, meaning that really Green's is a subcase of Stokes' theorem. All right, so that is going to be the last thing for this video. In the next one, we're going to discuss a corollary and motivate it using an example.